Hello, my loves. Welcome to our video for Unit 8.4, Quadratic Equations in Vertex Form, Part 1. Now, this isn't a normal video, and as such, I don't have a normal intro for you. Rather than teaching you something new, this video is here to summarize the key findings of what we discovered in class together the last time we met. So let's get right into it, and I can hopefully get you out of here as soon as possible. To set the stage, as we discovered back in class 8.2, there are diminishing returns with just plugging numbers into standard form when it comes to graphing quadratics. If we want to build the graph of a parabola, right, it's crucial that we find its vertex. The issue, though, is that it's not always obvious where exactly on the coordinate plane that vertex lives. This was the motivation behind us building our intercept form written out for you here, where we used the symmetry of the parabola to our advantage to place the vertex halfway between its x-intercepts. But good enough is never good enough for us mathematicians. So the idea behind the question we asked ourselves this time was, well, what if there was a form that told me exactly where the vertex was, without needing to go through all of that hassle of finding the intercepts first? This led us to our second and final form of a quadratic equation in two variables, aptly named its vertex form. And to find it, we asked ourselves a question. That question was this. Say that I take my parent graph, y equals x squared, my simplest possible quadratic equation. I want to see how making changes to that equation, in other words, transforming that equation, transforms the graph it produces. And to visualize these transformations, we used Desmos and played around a bit with a bunch of different numbers. The first thing that we tried was multiplying x squared by something. We called that something a, right? Just some constant. Now, if the value of that constant was really big or really small, it got farther away from 1, either a large positive or large negative number. The way that we worded that, we said it had an absolute value greater than 1. We saw that visually what happened here was that the graph of our parabola got taller. The formal definition for what we described here, if we're getting taller, we're pulling it away from the x-axis. It is being stretched out. And if it's going up and down, right, away from the x-axis, it's being stretched vertically. So this is what we called a vertical stretch. If the value of a was smaller, though, right, the closer we got to 0, either a small positive number or a small negative number, rather than getting taller, we saw that our graph was getting smushed towards the x-axis, and in so doing, it became a little bit flatter. Here, rather than stretching it vertically, we said it shrunk vertically. Our formal terminology that we used here, we called this a vertical compression. It was being pushed towards the x-axis. And last but not least, if the value that we multiplied by was positive, we saw that our graph was concave up. It was a happy face. But when that value is negative, instead of opening upwards, it became a concave down parabola. Our graph here was flipped over the x-axis. The formal word that we use here to describe a flip on a graph, we call it a reflection. So this gives us a reflection over the x-axis. Cool. After multiplication, we said, well, what happens if instead of multiplying, I add or subtract? And we saw there were two different places where we could do that addition or subtraction, either outside of the square or inside of the square. If I add or subtract outside of the square, if I'm adding something, in other words, the value being added to it, which we called here just some constant k, was a positive number, we saw here that the graph of our parabola was moved upwards by that value k. If that k was negative, though, in other words, if we subtracted outside of our square, here the parabola was shifted downwards on our graph. The formal word here, right, if we're moving up and down, we're moving vertically. And if we're shifting it, in other words, to say that I'm moving my graph is I am translating it on my coordinate plane. So here, these values of addition or subtraction outside of my square give me a vertical translation either up or down by k. If I add or subtract inside of the square, though, here, this, instead of moving me up and down, we saw move me left and right, and weirdly enough, it did the opposite of what we expect. Usually, adding something would move you to the right on the number line, but the way that we described it is we're actually counterbalancing the addition or subtraction. So if h is positive, in other words, if I add inside of the square, here, my parabola shifts over to the left to undo that addition. And if I subtract, rather than moving left, it's the opposite of what I expect. Here, my parabola shifts to the right. The way that we worded this here, right, left, and right, tells me that I'm moving horizontally, and our formal word for shift, right, we are translating. So here gives us our horizontal translation. Putting it all together, we get the vertex form of a quadratic equation in two variables, and the idea now is that we can break this into pieces where these values of multiplication, addition, or subtraction are responsible for different things. The way that we write our vertex form is as follows. Y equals some value a times the quantity x minus h squared plus k. This value a being multiplied by that square out in front is responsible for a couple of things. First of all, we saw that it gave us a vertical, which I often abbreviate by V. It gives me a vertical stretch. I pull away from the x-axis if the absolute value of a was greater than 1. We got a vertical compression, sometimes abbreviated as COMP for compression, if the absolute value of a was less than 1. And last but not least, we saw that we flipped or reflected over the x-axis if the value of a is negative. For our pink h here in the middle, right, here is responsible for our horizontal, which I abbreviate as h, translation. Here, if the value of h is negative, our graph moves right by h units. And if the value of h is positive, our graph moves to the left. And last but not least, this addition or subtraction by k outside of our square, this is responsible for our vertical translation. And here, if the value of k is positive, our graph moves up by k units. If k is negative, our graph moves down by k units. Very nice. And the thing that we noticed about this vertex form, the reason why it's called vertex form, is because these translations, h and k, match up with the coordinates of my vertex. So from here, my vertex lives right at that point, h, comma, k. By looking at the structure of the equation, I can now place exactly where my vertex is on my graph. Cool. The last thing that we did here was take a couple of examples. We wanted to state our transformations and then use it to find our vertex, our axis of symmetry, and our x and y intercepts. Let's do this first one together, and then I'll give you one more to try on your own. Y is equal to 2 times the quantity x minus 1 squared minus 2. Now for my transformations. The first thing that I'm going to do is look at my value of a here, which is 2. When I multiply by a large number like 2 that is bigger than 1, I know that this is responsible for causing a vertical stretch. I'm being pulled away from the x-axis here. We say that we're stretching by 2, right? By a factor of 2. So vertical stretch by 2 is how I would word what that 2 is doing. This negative 1 here, inside of my square, again, it's the opposite of what I expect. I expect a negative to move me to the left, but here it's horizontally going to move me to the right. So this moves me to the right by 1 unit. And this -2 outside of our square, the value is negative. So here's my vertical translation. When it's negative, it does what I expect outside of the square. It's going to move me down 2 units. My vertex, of course, I know comes from that -1 and that -2. If I started at 0, 0, and I moved right 1 and down 2, then I would end up at the point 1, 2. So 1, 2 is the vertex of my parabola. The axis of symmetry, right, I know it's a vertical line, so its value is always going to be x equals. And since it passes through the vertex, I take the x-coordinate of my vertex. X equals 1 is the equation of my axis of symmetry. To find my x and y intercepts, again, I know what to do. The x-intercept is found by plugging in 0 for y, whereas the y-intercept is found by plugging in 0 for x. Finding my x-intercept here is as simple as plugging in 0 for y. So let me do so. And now you'll notice I have a polynomial equation that I know how to solve. The first thing that I might want to do if I'm trying to get x by itself, well, let me begin by adding 2 to both sides. This tells me that 2 is equal to 2 times the quantity x minus 1 squared. Dividing both sides by 2, I can show that 1 is equal to x minus 1 quantity squared. Now I can't touch that -1 until the square goes away. I can accomplish that by taking the square root of both sides. The square root of 1 is plus or minus 1, and now I've got x minus 1 left over because my square and my square root cancel each other out. Now I'm in my funky split territory if I've got a plus or minus. So I know my answers are that x minus 1 could be equal to positive 1, or x minus 1 could be equal to negative 1. If x minus 1 is 1, adding 1 to both sides, x is equal to 2. If x minus 1 is negative 1, adding 1 to both sides, x is equal to 0. What this, of course, tells me is that the points 2, 0 and 0, 0 are the x-intercepts of my graph. I can do the same thing here for my y-intercept. I just need to plug in 0 for x. Well, here, let me take my equation in vertex form. X gets replaced with 0. If I can simplify the right-hand side, I get a value for y. Well, inside of the parentheses, 0 minus 1 is -1. -1 squared order of operations would give me 2 times positive 1. 2 times positive 1 is 2, and 2 minus 2 equals 0. Notice here, this should make sense. We found that the point 0, 0 is on our graph. It is simultaneously our x and y intercept. Cool. One more for the road. Let's try this one. Y equals negative quantity x plus 3 squared. I want to list my transformations. I want to state my vertex, find my axis of symmetry, and identify my x and y intercepts. Take 2 minutes, pause the video. Let's do it. Go. Five, 4, 3, 2, 1, and stop. Well, there are 2 things that are happening here. I have this negative sign, and I have this plus 3 inside of my square. If I multiply by a negative number in front of my square, I of course know that this is going to cause a reflection over the x-axis, right? So I'm now going to be a concave down parabola. It's a sad face. And this addition by 3 inside of the square, again, it's the opposite of what I expect. I think addition would move me to the right. It actually ends up moving me to the left by 3 units. From here, originally my vertex was at 0, 0. If I take 0, 0 and move it 3 units to the left, that would land me at the point -3, 0. If I want to make it really explicit, right, I could say there's an invisible plus 0 at the back there that corresponds to the y value of my vertex. The axis of symmetry, well, I know it's a vertical line, which is always x equals for its equation. It passes through the vertex, so the x value of the vertex gives me the x value of my axis of symmetry. My axis of symmetry appears at x equals -3. To find the x-intercept, again, I plug in 0 for y. To find the y-intercept, again, I plug in 0 for x. Here, starting with that x-intercept, I know that 0 is going to be equal to negative quantity x plus 3 squared. I can start by getting rid of this negative sign by dividing both sides by -1 or multiplying both sides by -1. Here, 0 is going to be equal to x plus 3 quantity squared. Again, I want to get rid of the plus 3, but I can't do so until I take the square root of both sides to cancel out the square. The square root of 0 is just 0. I could write plus or minus, but it's trivial. If 0 equals x plus 3, subtract 3 from both sides, x is equal to -3, which tells me here that the point -3, 0, my vertex, is in fact the only place where I cross the x-axis. To find the y-intercept, all I need to do is plug in 0 for x. So y is going to be equal to -0 plus 3 quantity squared. Well, I've got -0 plus 3 is 3. So I've got -3 squared, which is -9. As a point, that tells me that the point 0, -9 is on my graph. The only thing remaining for us to do is to use vertex form to graph, which is what we will see next time in class 8.5. But this is class 8.4, so until then, take care, be good, I'll see you when I see you. Goodbye.